Hello everyone, and welcome to this next term work on the V2 lab term work series, that is term work number 6. Let's discuss the problem statement. Here we need to compute the sin x by cos x, which is nothing but tan x, using the Taylor series approximation. And we need to compare the result of Taylor series approximation with the built-in library functions provided by the C programming language, and print the both result with the appropriate inferences, means some kind of difference between them. So computing sine of x divided by cos of x using Taylor series approximation is the first thing that we should keep in mind, and how to use the built-in function, that is another thing. So let's have a just glimpse over the Taylor series. You might have studied the Taylor series in mathematics of the first sem, or might be studied in your PUCs. But the Taylor series is simple. To give just a brief about it, uh, Taylor series for sin x is given by x minus x cubed by 3 factorial plus x raised to 5 by 5 factorial minus x raised to 7 by 7 factorial, and so on. The thing to be observed over here is the x is odd number power, that is the first term is x raised to 1 by 1 factorial. So the odd number power divided by that particular odd number factorial is continuing, and the sign of the term, that is alternating between plus and minus. First term will be plus, then second will be negative. Again, third will be positive, fourth will be negative. So the sign alternating is another point to be kept in mind. Whereas the cos x using Taylor series is given by the same, but here the difference is that it is even power, increasing even power for the x value. Like first term will be x raised to 0. 0 is also an even number. So first term will be x raised to 0 by 0 factorial. Then x raised to 2 by 2 factorial, x raised to 4 by 4 factorial. In both sin x and cos x, power will be increasing by 2, and like consecutive odd numbers and consecutive even numbers. These consecutive odd and consecutive even numbers will be the powers of sin x and cos x. We need not to go more deep into the Taylor series. This much information is enough for solving the problem. Another thing mentioned over the problem is built-in function. So three kinds of built-in functions we might be requiring in this program, that is sin x, cos x, and tan x. Actually, using the tan x only, we can get the result, because as we know, sin x by cos x is we can get directly by tan x. So just for introduction, I added these three functions are there. Even cos x, uh, cot x and cosec x, all these functions are also available. And another point is that these functions are defined in math.h header file. So we need to include that header file before executing the program, before writing the code. Just in simple sample input output, if the x is equal to 1 and x is this term, whatever we have given over here, that is sin x equal to x minus x cube. This x is nothing but a input for our program, that's it. Let's say input is 1, and using Taylor series approximation, what we get, that we need to print. After that, using built-in function, what we get, that we need to print, and we need to compare them and say this is the absolute difference between them. That's it about the program. And this is some sign function for calculating the what we say, the Taylor series expansion for sin of x, but we will not discuss it over here. I will discuss it while writing the code. So let's start writing the code. let's include the necessary header files. Let's say stdio.h hash include. As I told, for built-in function, we need math.h, so we will include that also. Once we have that, well, let's directly go to main function. There are some more functions required in the program. We will write it as soon as we discover them. As I told, x is the input. Here I will not take input from the user. I will just say double x equal to 1.0, because here our aim is not to take input from the user and all. Our aim is to compare the result between Taylor series expansion and built-in function. So we will not focus on other things much. And in the Taylor series, as you know, Taylor series is infinite terms. Like it, it is of infinite terms. But for our calculation, we need to have some boundary. So we will also take it as int terms. Terms is a variable which contains the number of terms we need to calculate in the Taylor series expansion. Let's say it as a 10. Once we have it, uh, we will be calling the uh, let's say we will store the result in uh, let's say my 10 result, and we need to call a particular function my 10. I will say my 10, which takes two parameter x, that is value for which the Taylor series expansion of tan of x is to be found, and number of terms means also needed, because we can the program can calculate for only finite terms. It cannot calculate for infinite terms. So we need to specify the number of terms also. And let's have the another variable which can hold the result, means built-in function result. Built-in function result, we can directly call it say tan of x. This will give the result. I will have some comment over here so you can understand. Taylor series, and here I will say um, built-in result. So this tan result will give built-in result, and my tan result will give the Taylor series approximation or Taylor series expansion. Um, let's first print the result. Once we get done with the main function, we will go back to the program using the Taylor series. We are just printing the results like what we have got from the Taylor series. It is percentage f. Yes, it is percentage f, and not like that. We will have tan of percentage f equal to percentage f. We will have a new line character. Two variables which we need to print. First is tan of x. Next one is my tan result. Yes. Let's copy the statement and write it same for the user defined. That is a built-in function. Built-in function tan of x percentage of, everything remains same, but only now we need to print the tan result variable. Once we print the result will be getting displayed. We need to compare the result of both these Means is there any difference between the Taylor series and built-in function result? Before that, we will just look over these functions. We will just complete these functions. First function over here is that is my10. That is user-defined function. So we need to define it. Double my10. I will say double x and int terms, because these are two variables which have been supplied as a parameters or arguments. Um, Return. I will return the sign by cos result, my sign of x comma terms, because here you can see I know how to calculate for sin x and I know how to calculate for cos x. So I will separately calculate the result for sin x and I will separately calculate the result for cos x. Then I will uh, find out the result. X comma terms, sorry, it was my sine of x comma terms divided by my cos, because sine by cos gives us the tan result, and same for here also, x comma terms, that's it. Yes, but again we need to write both the my sine and my cos function. These are not predefined or built-in function. These are um, user-defined function. So let's write my sine of uh, again same double x comma int terms. Yes, here I need to generate this pattern x minus x cube by 3 factorial plus x raised to 5 by 5 factorial. That pattern I should generate over here. Let's write. First what I will do is x equal to um, there is a concept called normalizing x to the range of 0 comma 2 pi. So if you are a little bit familiar with the um, little bit familiar with the Taylor series expansion, or like other series, mathematical series, which are helpful for finding the trigonometric result, then you will come across these terms, that is normalizing. Basically, we are setting the value of x so that it can be in the range of 0 to 2 pi. So how do we do it? We use a f-mod function. F-mod function is popularly known for finding floating modulus. Floating modulus is like um, um, it helps in normalizing angles to specific range. If you want to normalize or convert an angle between 0 to 2 pi or minus pi to pi, minus pi to pi. So this can be done using f-mod function, basically used in most of the trigonometric calculations. So you need not too much worry about what is normalization or other things, because these are mathematical concept, mathematical things which we need to do in order to get the desired result from the Taylor series expansion. So if you are understanding how the logic is working, that's completely fine, and you need not worry much about the what is normalization, how it is happening, all these things that you will be learning through the mathematics class. This is what I have done here. That is f mod x comma 2 pi means we are normalizing the value of x from 0 to 2 pi. But here you can see the pi is highlighted with underline because pi is not defined. So let's define the value of pi as a global constant. Uh, Pi, let's say, give some value 1415. You can specify it even more. That's also fine. Once we find out the value of x, uh, have some two variables. Let's say one to hold the result, double result. We will say the result is initially 0 because now we are going to set up a for loop where this result variable is going to be modified. and we will be calculating the each term in the series using double term equal to x. So term is like we can see here, this x is particularly one term, minus x cube by 3 factorial is another term. Means each yeah, each number in the series or each term in the series we are going to get by we are going to store in the double term x. Initially it will be x in the sign, so you can see here x. So initially it is x. We will keep on changing it using for loop. So let us set a for loop. The for loop should be int I equal to 1, I less than or equal to terms, because it should execute as given number of terms I plus plus, simple for loop. And here we are adding the result, we are adding the each term to the result. Like I calculate the x, I will add it to result. I will calculate this minus x cube by 3 factorial, I will add it to result. That is the thing we are doing over here. Result plus equal to term. And how do I calculate the term? Term into equal to means I am multiplying the previous term to the some value. What is that value? Minus x into x, divide this by a factorial value. How do I get the factorial value? I will explain this once again. 2 into n. After that, I need to have again a multiplication of 2 into n plus 1. Uh, here n means not n, exactly it will be I, because we are not taking any specific n number over here. N will come in the formula, in the program it is I. Yes, 2 into I into 2 into I plus 1, yes. So how it is working? We are iterating for uh, I equal to 1 to I less than I less than or equal to terms, means we are executing this for loop as number of terms as we want in the Taylor series. That's first thing. We are adding result of each term. We are adding the value of each term to the variable result, because the result will be holding the complete value, whole value of the Taylor series expansion. And how we are calculating the term? We are calculating it by multiplying it to the previous term. Let us see here. You have x. How you will be getting x cube? You just need to multiply x squared to this previous term. Here also you have x cube. How do you get the x raised to 5? Just multiply x raised to 2, that is x squared to previous term. So we are doing that, minus x raised to x. Why minus? Because sign needs to be alternating for each term. Like if the previous term is positive, it should be negative for next term. If the previous term is negative, it should be positive for the next term. So for that we are adding minus x into x. This divided by we need to have the factorial. But what is this 2 into I into 2 into I plus 1? Just assume I just go on adding 1 for this I. Let us add 1. 2 into I, that is 2 into 1 into 2 into 1 plus 1, that is 2 into 3, means 6. 6 is nothing but the 3 factorial. So how we get the value of 3 factorial? Means odd number factorials, we can get them using this. And x raised to 5 by 5 factorial. Make the I equal to 2, because after a single loop, the I will get increased to 2. So in the second iteration, I will be 2. So 2 into 2 into 2 into 2 plus 1, that is 4 into 5. Yes, 4 into 5, that is 20, which is nothing but 5 factorial. So these are some like short trick, like mathematical trick to find out the factorial of consecutive odd numbers in increasing way. So uh, that's it what we did it for finding the term. Um, Once we do this, the result will be getting stored into the result variable. After this, for loop return the result. Uh, yes, I think it is correct over here. That is, we have successfully found out the uh, Taylor series expansion for my sine function, which is nothing but sine of x for given number of terms. Why I copy pasted is that we can design the cost function in the similar way. Just you need to change the name, and f mod also remains the same. Result term variables also, but the term variable for sin x was x, for cos x it is 1, so let's change it to 1, and so double it is, let's say 1.0. Int I equal to, here you can see x raised to 0, it starts from x raised to 0, not from 1. In sin x, x raised to 1 was the first term. Here x raised to 0 means the power starts from 0. So let's start I equal to 0. I equal to 0, I less than, sorry, what is, I equal to 0 and I less than terms, because we are not going to nth term. We will be going till n minus 1th term. If n is the number of terms, we will be going till n minus 1th term, not to nth term in the cost function. And result plus equal to term into equal to minus x into x divided by, here uh, 2i into 2i plus 1 gives us the odd numbers. How to get the even numbers? 2i plus 2 and 2i plus 3. 2i plus 2 into 2i plus 3. That's it. This will give us the my cos function, and my sine my cos function together will give the my tan function. My tan function is getting called over here, and anything remaining over here is the comparison. Let's have some comparison. And printf absolute difference. Absolute difference means a difference between two numbers irrespective of their sign. Like difference between 1 and minus 1 is not 0, it will be 2. Means if you actually try to add, it will lead to like 0, but difference between minus 1 and 1 will be 2. Like that kind of um, a result we want. Actually, difference percentage of, let's have backslash n. Yes, for finding the absolute, there is function called fabs, which gives us the floating point absolute number. Because absolute function gives takes only integer parameter, fabs for floating number, because we have two variables, both of floating number. My tan result, um, hmm, my tan result minus tan result. I am subtracting the my tan result, that is calculated using user defined functions, and tan result that is calculated using the inbuilt functions. I'm comparing and I'm printing the result of, sorry, a difference of both results. So the program is done for now. Let's execute and see if any mistakes are there. Yes, you can see. Using the Taylor series, we have got um, tan of 1.0 equal to 1.0, and using built-in function, we have got tan of 1 as 1.55, and the absolute difference is coming to be 0.557. You can increase the terms and see you will be getting more accurate result, more precise result. You just need to increase these terms and try with the different value of x in order to better understand this program. And also, if possible, calculate it for manual and compare it with programs output. Uh, I hope you got the concept of the Taylor series approximation implementation using C programming and also the built-in functions available for the trigonometric functions. Thank you.